So here we have Sri and Yuan. I'll let them introduce themselves. But what I like to do in panels like this to kind of bring these things to life is discuss interesting factoids about the people on stage. They're not just amazing engineers and brilliant scientists and technologists. They actually have interests outside all of this. Sri, specifically, is on a mission to visit every single national park in the US. And I'd like to get an update from her once a year. So Sri, where are we on that checklist?
24 and counting.
24 out of 63, okay. So you're very busy at D-Matrix, so you'll not be doing any this year, right? You have a lot of product to ship.
That's right. This is the most exciting year for us. All of our hard work over the few years is now coming to fruition. Our first product is about to ramp up to mass production very soon, and we're going to unleash it into the wild very shortly.
And wait, what do you specifically do at D-Matrix?
So I head a product at D-Matrix, so I'm the dangerous person defining what needs to be done and defining the strategy, working with our customers, and more importantly, working with our engineering team, which I totally love.
All right. Yuan, what's an interesting factoid about you?
Me? Okay, so I grew up in China, so I came to US for the graduate school, and so I spent almost my entire career and working on distributed systems. And so at some point, about 10 years ago, I got into AI when I joined Google. And so at that time, my boss was Jeff Dean, and he was just starting the TensorFlow system.
Yeah, Yuan is kind of a big deal. But what I love about your answer is when I asked you a factoid about your outside work interests, your outside work interests are your work interests.
This is my work interest.
You're a nerd's nerd. That's awesome. Yeah. All right, and so you're a technical fellow and architect in the core AI group in Microsoft. What does that mean?
Well, I mean, I lead the Microsoft AI Frameworks team. The team is responsible for pretty much optimizing getting the most efficiency out of the most important models Microsoft cares about. And also this is also the same team is also responsible for building the entire software stack for Microsoft AI accelerator, Maya. So that's roughly the team.
And what is your intersection with D-Matrix?
That's very interesting. And one place we have been spending a lot of time optimizing the OpenAI models. And at one point, as you know, the model becomes more and more multimodality. And typically that means the models contains various parts of the computation. Some computation can be offloaded to a specialized accelerator. And so this is where the D-Matrix accelerator comes in.
You found the accelerator you've always been looking for, basically.
We know we want to specialize. We know we want to get there. And at some point, and my friend Michael introduced me to D-Matrix, and so we met with
Michael Stewart, investor with M12, Microsoft Venture, somewhere here in the audience.
Yeah. So
all right.
Yeah.
So before we go in there, basically the topic of this panel is AI infrastructure of the future. So kind of to paint the landscape, AI infrastructure is the unsexy bit of AI, but that's where all the magic happens, actually. That's where the magic is enabled. It starts at the foundry level, how we build chips, what materials we use, what technologies we use, testing the limits of physics, and then moving up the tech stack to how we build the actual processors, what computer architecture is used, then how we stitch those processors, say through chiplets or whatever other technology, onto boards, into systems. We connect them through networks and into racks, and we scale up and scale out. So there's a lot that goes there, and then we get into the software as well. At Playground, as you can tell by now, we love to operate at the boundary between atoms and bits, and so therefore we love infrastructure, because it's where hardware and software come together for an optimal stack. Once you get into the software, you get into issues like compatibility and open and proprietary approaches, abstraction layers, all these things that impact how the magic of generative AI is actually delivered. So what we hope to cover right now with our experts here is tease apart those layers and discuss what we have now, where we need to go, and what's going to happen in the next decade. So Yuan, I'll start with you. Before we talk about the future, can you give us some historical perspective of AI infrastructure and how we got to where we are today?
So, and I still remember, I think in 2021, and our Microsoft CTO, Kevin Scott, called a few of us and told us, hey, there's a very amazing model coming from OpenAI. But we want to make it available to every customers, but then there's a small problem, and running it is hugely expensive. So this is the journey started. So in some sense we were a few years ahead, Microsoft a few years ahead of everyone, and we saw the model in 2021, and we started to optimizing it and trying to get it into the products, the GitHub Copilot and the M365 and all the interesting places. So initially, we spent a lot of time working at the hardware layer, so optimizing it for the NVIDIA GPUs and then try to get the AMD GPUs, ported it to the AMD GPUs and get it into the production. And we did all this. And also in the meantime, and building our first-party accelerator, trying to get the models running on our first-party accelerator. So, and then we take a step back and we look at the problem as a whole, and then we say, hey, this is really it's a distributed system problem. It's a large-scale distributed system problem. It's really, if we really got the full efficiency out of the inferencing, and you need to make sure your load balancer is working really well, and so your resource management layer scheduling is, your fault tolerance, reliability is there, and also there's ideas of how the computation can be specialized, and then you need the disaggregation. Really is a long learning process, and I think at this point we have a reasonably good understanding of the computation, and from there we also know what kind of hardware we need to build in order to support it.
That's an interesting historical perspective, because it starts at an OpenAI model shows up and you have trouble basically running it cost effectively. And thinking about D-Matrix, and I'll let Sri talk, that was before your time, before you joined D-Matrix. Of course, as a VC, we have to project into the future. What is that workload going to be that we need to design the future for? What are those processes? Because GPUs will not scale because of power and cost issues. Existing processors cannot address this new workload. So before the OpenAI models came up and the ChatGPT moment, we had to invest in D-Matrix and say, the workload of the future will be, we called it NLP at the time, or language models. And I'm glad that that was the first problem you encountered in your AI infra, because that's exactly why we invested in D-Matrix. And actually, I'll let you, Sri, now talk about how D-Matrix is going to address this problem in the next 3 to 5 years.
Yeah, so I'll pick up from where you left off, as in where you invested on NLP being the starting point, right? Back then, BERT, which was one of the biggest models in the day, was getting used in things like Google search. 10% of search was starting to get used with BERT and accelerated with BERT. And so we were going down that path, and it was so exciting to see a transformer model starting to do something useful. And that's when we unpacked that whole model. You've got, it's always about compute, memory, and networking, and the balance of these three things. And it shifts with every workload. And with this particular class of workloads, it's all about the memory bandwidth, right? You've got a workload that so far everybody tried to optimize for compute. You've got something that's now going to stress the memory bandwidth. It hits the memory wall. So we had to build a whole lot of ingredients around addressing this fundamental pain point and breaking through this memory wall. And so a lot of time was spent on building that technology and really getting to the point of building in-memory computing capabilities, bringing that memory compute integration to get to that efficiency. Because what you end up doing, what Yuan was saying, is basically you end up wasting GPUs, wasting compute. And if you look at the amount of energy and the cost it takes to run these data centers to serve these models, it's just completely unsustainable. And we're on a mission to make generative AI sustainable, commercially viable, right? So, and going back to what we are doing to make it efficient is not just the in-memory computing piece, it's around numerics and innovation in the numerics where you can have more compressed formats for inference. Again, we focused a lot on inference. I think that's pre-ChatGPT, people didn't know about it. Then ChatGPT happens and it's like, oh, look what d-Matrix is building. And then very recently, DeepSeek happened. And people were talking about inference time compute and changing of the scaling laws from training, and it's shifting to an inference scaling law. So now we're starting to see a lot more can be done with inference time compute and inference time scaling, where you can actually get a lot better in terms of model quality and performance out of spending more time and more tokens. So it's reasoning and it's agentic and all these, you talk about what's the emerging thing, it's going to be new paradigms of deployment, new ways, like there's going to be new experiments, and people are just getting their hands on, hey, this model can do these cool things, how can I now apply it? And we need to be ready for a very fungible future of where people are going to do a lot of things over the next 3 to 5 years, trying a lot of these things, and then figuring out what's the best fit. And to sustain and enable this kind of innovation, you need compute that is efficient and that's accessible and affordable. And our goal is hopefully that we will have enough accelerators beyond d-Matrix that does that, and GPU alone is not sufficient. So it's a long answer to where we started to what I see the next 3 to 5 years kind of going.
No, that's great. But from the hyperscaler point of view, d-Matrix is addressing a specific type of workload and a specific problem, but hyperscalers think more broadly about AI infrastructure. So what would you have to add there?
Well, I mean, as we know, I mean, if you look at, as you mentioned, DeepSeek models, you mentioned about, there's OpenAI models, Anthropic models, and there's Gemini. So the models looks like it's getting competitive. And so the real differentiation is going to be the AI infrastructure. It's where the efficiency comes in. And also as we're going, if you look at the scale, and so OpenAI is hitting like 500-600 users, daily users, or something, monthly users or whatsoever, and also we're experiencing is very, very exponential growth in terms of the user. So the scale is there, and also one of the key problem we have to deal with is the reliability, and also to how to get all the accelerators the utilization, and sometimes you can optimize the things on a single device and make it very fast, but somehow when you deploy it at large scale, the utilization becomes really is many problems, like the time zone problems, there's the load balancing, and also the SFA, we need to over provisioning, and there's many these kind of problems that at the hyperscale, and we have to deal with.
Yeah, no, I'm glad you mentioned scale, because data centers are blowing past gigawatt scale, hundreds of thousands of processors. I mean, we're going beyond the limits of what you can even reasonably manage, and with failovers, not just from rack to rack or server to server, to building to building, and
Yeah.
geolocation to geolocation.
Yeah.
Maybe Sri, you can address, like, you as a provider into a data center, how do you have to think about that problem?
So I think when, like, going back to what you initially said in infrastructure, it's like a full stack all the way down from like the semiconductor all the way to the systems level stacks that Johan and his team are building. So for us as an accelerator company, we focus on the compute. We're working, obviously we're going to do the best to make the best, most efficient compute, the most performant, reliable. So there's things we control in this, in our, like I would say, the product that we built. But then there's all the work we have to do in integrating with the ecosystem, collaborating with them. Like inference today is inherently distributed. It's just, you've got to know that. It's not like before where you put many models on a single card, and you've come from that place in the last few years to where you need many, many racks of GPUs to actually run inference at scale. And so being able to plug in to a data center infrastructure and allow for seamless integration very quickly into the software stacks, making sure that we can plug and play into the scale out and the scale up ecosystem. So less exoticity and more standardization, I think, is going to help us. I think there are things emerging in the ecosystem where people are starting to look at, okay, how do I standardize on scale up? How do I standardize on the scale out networks? How do we standardize on more of these? And we are big fans of standards because that allows, again, us to plug and play into this ecosystem in a seamless way. And then really at the core of it is the innovation at the compute level, right? And that's where the efficiency goes back in terms of performance, the TCO and optimizations, and unlocking that through whatever the data center infrastructure operators want to do. We're not the operators, so we want to unlock that so that the end customers and end users have fun building the applications. So I mean, I want to hear your perspective, Johan, in terms of how you'd like accelerators to play nice with what you're building at scale.
So the one thing which is I mentioned already is specialization. And I mean, unfortunately, specialization is hard to do because you don't have the crystal ball of the future. There's a long development cycle. But on the other hand, this is what we typically call a hardware lottery. And if you bet on something and you hit the ball out of the park and you win the lottery. So the interesting thing is, if you look at the models, and so this large language model based on the self-attention and also MOE, and so it's relatively stable at this point. And in some sense, actually, it's a good time for the Harvard startups to think about how to specialize, near memory compute and also in-memory compute, and to deal with, the decoding phase. And so how can we? The efficiency is most of the efficiency comes from the specialization.
Yeah, I think it's good he mentioned mixture of experts. It's like not only the models are going to the mixture of experts, it's like the infrastructure is going to a mixture of experts.
Yeah.
And actually, the fact that you're looking for specialization. The other thing I think that's happening, just in my past experience building accelerators and trying to ship it to end customers, there's this barrier to entry saying, okay, you need a certain ROI to kind of break through. What I'm observing is that the cost of compute, the energy behind it, is now so high that that barrier became so much lower. So this is a great time indeed for a lot of accelerator startups to thrive. And this is a very exciting time to be in this space.
Yeah, no, actually there was an excellent insight buried in there that you kind of sped through. Speaking of mixture of experts, we're all familiar with mixture of experts architecture for large language models, but what we're seeing is a mixture of experts at the hardware level. That's what specialization means. An accelerator per each phase in the AI workload. That's another form of mixture of experts that people are not talking about, and I'm glad you brought it up. That's actually a cool insight. So is disaggregation of compute the future of the data center for the next 5-10 years?
if you ask me, the answer is yes, and we need to disaggregate. Yeah, so that allows us to dynamically load balancing and dynamically, the allocating the resource. The workload is going to get more and more dynamic.
So is the challenge there utilization then? Because every accelerator has to be sufficiently utilized. It has to justify its existence.
This is a very good question. So it's actually more than just utilization. So say, for instance, we know that the current computation is basically as what we call it, there's two phases. One is the prefill, the other is what we call decoding. The prefill is compute bound. The decoding is a memory bound. And so right now we're running the whole thing on one accelerator, and also which one you want to optimize, which phase you want to optimize. But if you disaggregate, and you can actually imagine you can build a specialized engine for prefill or a specialized engine for decoding. And that's going to not only the utilization and also the efficiency in terms of power consumption and performance is quite intriguing.
Yeah. Actually, that's an interesting thing, this push and pull between compute-bound and memory-bound workloads, but D-Matrix has an answer.
Yeah, actually, this is very interesting. I want to point out there was a nugget in there that you once said, right? Like, heterogeneous compute has been around for a long time. This is not something new in terms of disaggregated or heterogeneous compute. What we're starting to see is that, like, the workload patterns, within the same workload, you now have different behaviors. That workloads are themselves getting partitioned, and there's heterogeneity in terms of compute within a workload, so which is like another level of disaggregation. And going back to what Yuan was saying is that the decoding phase is memory bound, right? You then don't want to utilize a piece of compute that is not optimized for that. And like I said in the beginning, when we did the whole analysis around the memory wall and how to break through it, we've got a very unique piece of memory compute integration and a solution around it that allows us to really solve this problem. Not only just an efficiency play, as in like we can utilize the compute really efficiently, but because of the physics of this, we can go 10x faster than what the GPU is, right? So it's not around just the efficiency, utilization, and energy, which is great from a data center operator, but for unlocking it for end users from an interactivity perspective, which is what the future of AI workloads will look like. We're doing both and not compromising on that because we're not moving bits over a distance anymore.
Yeah, so one thing I should add, there's no free lunch here. And once you disaggregate, and it's becoming there's a lot of system problems you need to solve. And for instance, what will be the ratios between the prefill node and the prefill workers and also the decoding workers, how to balance the two, and there's a lot of it's again. So that this is my background is on distributed systems. I think if you look at all the problems we're solving, at the end of the day, it's becoming a distributed system problem.
Yeah, your 100,000 processors becomes 200.
Exactly.
Just there.
Right. And also it's heterogeneous, and you don't know what will be the ratio when you build a data center.
Yeah, what's the ratio, exactly. All right, so you both have to, you're building a multi-generational company, you're building data centers for the future, that have to last a long time and serve workloads forever, basically. How do you think about the future and what problem to solve for? I understand the disaggregation part, but, models will change eventually. We're going to find much different, much better, I don't know, ways to do things. So how do you think about that when you design your roadmaps? Maybe.
Well, this is the hardest problem, and frankly speaking, no one knows the answer, and as we don't have a crystal ball to the future.
Well, I'm asking you what to invest in, basically.
Yeah, so I think the short answer is, and in the design, we need to do as much late binding as possible. So that is the key, and shorten the development cycle. That means you can have some visibility about the future.
Shri?
So the way I think about it, because we build compute accelerators, is two very important. Obviously, we need the performance and the TCO, energy, like those are the core things. But the more critical thing is this ease of deployment and ease of use. So if the data center operator wants to just plug in more compute, it should just plug and play seamlessly in that ecosystem. So how can we make it very simple? The thing that people like associated with AI is like this is a very fast-moving, dynamic ecosystem. Things are changing a lot, but the data center isn't a fast-moving, dynamic ecosystem. It's actually a fixed physical entity with fixed racks, fixed hardware, like he's saying, fixed ratios of compute. So being able to unlock that value for infrastructure operators, systems engineers who are optimizing system level, and allowing that innovation to get unlocked and like the workloads and the apps, it's like we've got to kind of strike the balance. And I think the way we approach it is basically extract the most value with the specialization we offer it back to the operators, give that interactivity advantage back to the users, minimize the disruption in the data center itself, which is actually, it takes time to build and maintain and sustain.
All right, to wrap things up, back to sexy and unsexy. What's overhyped, what's underhyped in the AI infra space? Shri, maybe you can start.
I mean, I think the models that get the most attention. Like everybody's excited and talking about the next big thing and the cool things that it can do. But it's always the infrastructure that powers it that gets the least visibility, and it's the most unsexy thing to talk about.
So for me, as I would argue the custom silicon is overhyped. And so it looks like everyone has a shiny toy and they're trying to say, hey, my toy is 10x better than anybody else. But the reality is, there's one lesson I learned. That even in the existing NVIDIA system, there's a 10x there waiting for us to, efficiency for waiting for us to
We'll just
harvest.
make it happen faster.
Yeah, but I mean, it doesn't mean,
Yeah.
the custom silicon
That's right.
is not important. It's super, super important. That's the added differentiation when everyone does very good job on the inference, on the stack.
All right, well, we're going to wrap it up here. Thank you so much for your insights. You are in the trenches, working on this every day.
Thank you.